So now we can take a look at what is needed in order to implement the fetch microstate. And so at a high level, what we need to do is understand that the fetch microstate is going to be used to retrieve instructions from the memory address that's pointed to by the program counter. And this is going to be read from our instruction register. And so this will increment the program counter to enable us to retrieve the next instruction. So we'll need to send the program counter to memory. We'll need to read the memory contents, bring the memory contents read into the instruction register, and increment the program counter. And so in order to accomplish this, we have 4 different cycles that can be done. We have IfEtch1, which will read the program counter onto our memory address register, and then IfEtch2, which will read it into our instruction register, and then we'll read from the program counter onto register A, and then we'll increment and store that back onto the program counter. And so we can consider that we could simplify this in the following manner, in that the instruction for reading from the program counter can be done in the same cycle. So we are able to read from the program counter onto our memory address register, and then also read it into our A register. So this allows for us to record both the memory address register as well as the A register within the same clock cycle. And so what exactly is needed in order to add in all of the appropriate control signals for the IfEtch? For IfEtch1, we'll have appropriate control signals for the program counter, memory loading for memory address register, and loading for our A register. For Fetch2, we'll have control signals for memory as well as for the instruction register. And so for Fetch3, we'll increment the value and store that onto the program counter. And then we'll have appropriate control signals as well for our ALU as well as for our program counter. So these are providing for appropriate modifications for our fetch microstate in the same format. And we can treat memory here like it's a level trigger. And so we just need to tell memory to put its output onto the bus and record that into the instruction register. So then we can tell the ALU to add 1 to A and put that on the program counter and then onto the bus, and we've completed our microstate. And so how would this look in our diagram? So here we have a pretty detailed diagram showing all of the activity that's going on, from loading into the program counter, loading into register A and B, and also into feeding inputs into our ALU as well. Now at the end of clock cycle, we have here represented in green all of the values that can be seen in the program counter. And so here we see that a lot of the registers are able to see the values on the bus, but they ignore it because they don't need to make use of it just yet, except for memory address register and the A register. So by the end, and so here we're able to increment the program counter plus B, and then that is stored into memory as well. memory into the program counter. And so here we see that the values on the bus are easily read by other registers within our diagram. And so what happens by the end of our clock cycle? At this point, we want to add all of the places where the program counter values need to show, and that is represented by what we have here in red, where we've been able to increment the program counter. And we're wanting to transfer the contents of the ALU onto the bus. And then we want to tell the ALU to calculate the PC plus 1. Then our appropriate value can be stored in the program counter as well. And so once we've completed the fetching, we want to be able to decode it. And so after the IfEtch3 microstate, we'll transition into the decode microstate. And some things to keep in mind is that the decode state is a multi-way branch. So we can't encode this in the next state. And in this microstate, we want to make sure that we are able to examine the contents of the instruction register, specifically focusing on what the instruction will accomplish and focusing on bits 31 to 28. So once we know the goals of the instructions, then we can put that part of the microprogram and implement it for this particular instruction. So decode is going to act as a multi-way branch, and it's going to be based off of the available opcode. And so in order to accomplish this, we'll use the same approach as we did for the branch is IfEqual. And so on the last step of IFETCH, we'll set the top 4 bits of our ROM address to the opcode that's in the instruction register. And so how is that accomplished? So in here, we'll have the M bit, we'll add a T bit to the ROM, and then add the T bit and the Z bit to become the 6th address bit. And then we'll add an M bit to the ROM, and the M bit and the opcode from the bits also become the 10th through the 7th address bits. And so once that is accomplished, we can then set the appropriate M bit for our multi-way branch. And so our next state after the last state of the fetch will include the new addresses for each of the instructions. And so here we have our base addresses in the next state. So we have our base addresses for our add instruction, for NAND, for our jump, as well as for halt. And so here we're able to see the contents that are stored on ROM. We have the start of our execution sequence down to our IFETCH clone. This is providing our depiction of the multi-way branch for the IfEtch3. This will go to one of the available places that it could for IfEtch1 or IfEtch clone. This as well as for our, our branch of equal 4. This doesn't necessarily require that we use the 1024 words in ROM, but it provides for a good depiction. And so our next state is providing for our add instruction and how that is stored. And so for our add instruction, it provides for storing it into A, and we have our appropriate control signals. And then for add to, we store it into from Z to B with our control signals for our register and loading into B. And then we have our add instruction 3, where we're adding the contents of A and B and storing into X. And then we have our appropriate control signals as well. And so given the execution state for our add instruction, what would we need to change in order to create a NAND? And in this case, we can use our JLR instruction in order to provide for that. And so for what we are able to do is implement the JLR, where we store from the program counter onto register 1 into register Y with our appropriate control signals. And then we can also store from register X onto the program counter as well. And so this provides for another method for implementing our JLR instruction. And so here we've provided for one approach for implementing our control unit design. There are different approaches that we can take. And so with our microprogramming style, we've been able to design the appropriate control unit. And this has benefits in that we're able to provide a microprogram design that contains our control logic unit and also contains our appropriate components for ROM, and that can lead to better maintainability. However, there are problems and issues that can arise. So in order to solve problems associated with this being too slow, we can provide for a prefetch of appropriate micro instructions. There's also problems associated with too much memory being required. This allows for us to or the opcode with the next state value. And this can be done instead of prepending it. We can use more than one ROM as well. And that one set of ROMs can be used for which the state comes next. One for what the control output should be in the next state. And so in this example, we have a 3-ROM microprocessor that could be utilized. And so instead of adding extra bits to the ROM address, we can allow the next state to be chosen based on the state that we want to take from the multiplexer. So ROM is going to have 16 values, so we can choose the next state based on the first state of the opcode that is in the instruction register. So instead of adding to the address bit, we can choose the next state that is available in ROM. So there are some appropriate considerations that need to be made with regards to space and time. So with the flat ROM, we have more space. This is because we've increased the ROM by a factor of 32, and that can result in additional address modifiers, but then we have extra ROM space. This can be faster since only ROM access is needed in each micro instruction. So with regards to time, you want to be sure that the control signals that are generated can be used to address ROM after each delay has been referred. And this can allow for more efficient access time to ROM. There is also a time penalty that could be associated with it as well. And this can result in an inefficiency related to space. And so you want to ensure that each state machine can be represented as a sequential logic truth table. This allows for us to implement using normal combinational logic or using FPGA. And so with this, some logic functions can be seen as more efficient than a truth table. So if we were to implement these components using Boolean logic, this allows for appropriate control signals to be relegated using combinational logic circuits. And so some factors to consider when considering both microprogram versus hardwire approaches. With microprogram, you have the pros being simplicity, maintainability, flexibility, and rapid prototyping. While with hardwire, it's amendable for pipeline implementation, and it also allows for potential for higher performance. However, some cons include potential for space and time inefficiency with a microprogram control regimen, but with the hardwire, it can be potentially harder to change that design uh, for a longer design time.